Good evening.
Good evening. So, hi everyone. So, this is the live interactive session for week 10 for the course Structural Geology, and today's topic of discussion is brittle deformation, fractures, joints, and faults. My name is Rajiv Mukherjee, and I am currently hosting these live sessions. And we have already been covered 9 weeks. This is the 10th week, and we are left with 2 weeks of discussion sessions only. So this is the course outline as we have already discussed. So this is week 10 and we will be discussing about brittle deformation, fracture joints and faults. And on the 11th week, we will be dealing with the concepts of ductile shear zones. And today is 28th September 2024 and this is the 10th week. And let us start. So about week 10's content. So to summarize what we have learned on week 10, so it was mostly concepts of structures and joints, their geometric classification and distinction, mechanism of fracturing, relation between cohesion, internal friction, confining pressure, and deviatoric stress to produce fractures. Then comes the choice of failure models to describe the fracture geometries like Moore-Coulomb fracture criterion, von Mises fracture criterion, Hoek-Brown criterion, and their comparison, relation between mechanical anisotropy and differential stress and initiation of slip along fractures in layered rocks like shales and gneisses, etc. Opening of cracks and their mechanical classification like mode 1, mode 2, and mode 3 cracks. Variation of joint surface geometry with differential stress and fracture propagation velocity. Occurrence of joints and fractures in fields, relation and relating fracture mechanisms with tectonics. Then comes the concept of faulting, classification and geometry of faults, concept of net slip on fault surfaces, distribution of faults according to tectonic regimes, and then finally origin, growth and propagation and termination of faults in different tectonic settings. So keeping the idea behind the summary of week 10, we will be having today's discussion session on mechanisms of brittle deformation, fractures, faults, and joints. So let us start our conceptual problem solving class. So this is the first question which asks that which of the following type of rock is likely to occur or be associated with joints? Option A, pseudotachelites, option B, migmatite, option C, pegmatite, and option D, apatite.
It will be C, pegmatite.
Exactly. So if we then to solve that why it is pegmatite, then we have to see what are the other kind of rocks, right? Like pseudotachylite or pegmatite or apatite. Now the concept of joint is that it definitely is a fracture plane. It is definitely a fracture plane, but with negligible fracture parallel displacement. The joints are essentially cracks. Any crack can be a static crack, right? So a fracture is essentially a plane of discontinuity within the material or at an interface of a material. So fracture essentially is a discontinuity or the loss of cohesion in an intact material. It can either be an intact interface or it can also be an intact bulk material. So wherever there is a loss of cohesion, that will definitely be a fracture. But joint plane is in the sense that it is not a typical fracture, because in geological context, fractures do produce faults and do produce displacements along the fracture plane. But joints are essentially cracks, and most of the joints, they are the results of tensile stresses, whereas there are few limited exposures where we get conjugate joint sets that are responsible that are produced because of shear fracturing, right? So since joint is a static crack, you can say that it is a static crack. A weak plane within the material. So because of the inherent weakness, the joint planes may or may not localize deformation, but joint planes accommodate or do accommodate fluid injection, fluid intrusion in the host rock. So hydrothermal fluid intrusion will produce an acidic environment with negligible differential stress, and therefore large grain size or large grain sized silicate minerals can crystallize to form pegmatites. However, on the other hand, if we talk about pseudodactylite, these are the signatures of extreme pulverization and frictional melting, which indicates these are associated with brittle faults. Right? Now the thing is, migmatite is a rock that is associated with uh, granulite facies. So in granulite facies, you will not essentially get faulting or joints because it is entirely in the ductile regime. So migmatite is also not an option. Xerotachylites are associated with fractures, but the fractures which have high rate of displacement, that means which are faults with high rate of displacement, so that will be producing extreme pulverization, and in turn it will be creating xerotachylites. So option AB is not correct. However, if we talk about apelite in certain cases, apelite can also occur as dikes, dike intrusions, and therefore, in order to intrude into a host rock for a dike, they must require a weak plane or fracture plane. So in that case, aplites in the form of dikes can also run along the existing joint planes, right? So there is also a possibility of for the occurrence of applied dikes parallel to conjugate joint sets, or even in extensional joint sets. We can may or may find applied dike. However, pegmatite is a more common occurrence than applied, so that is why pegmatite will be the safest option to check in this case. However, applied is also not totally incorrect answer. Applied can also occur as dikes within existing joint sets. Applied is applied is basically the hyperabyssal form of granite. So we have the volcanic equivalent, which is rhyolite. The plutonic equivalent is granite, and the hyperabyssal equivalent is applied.
Sir, it can be said that these A, B, and D, these three rock types
Hmm.
are fine grained rocks. And in fine grained rocks, there is a
Hmm.
visible joint sets are not easily possible. And in pegmatites, the coarse grained rock, then its joint sets uh, presumption is more frequent and is more visible.
Yes, it's that logic can also be said, but the thing is, pseudotachylites is not as cannot be associated with joints because pseudotachylites itself cannot form joints. Pseudotachylites are always occurring in small patches and veins within within a fault core zone, right? So pseudotachlite cannot be massive in terms of their field occurrences. Pseudotachlites are not even massive. They always occurs in veins and pods and very fine thickness of material. So yeah, joint cannot form within them. Migmatite, it is a completely layered type of rock, and since it produces in high pressure, high temperature metamorphic facies, jointing or any sort of brittle deformation is not applicable at all. Now for applied, we can say that not in terms of their grain size, but we can say that applied occurs at much higher depth, right, than uh, pegmatite. So with higher confining pressure, and also applied, since applied is basically residual of a granitic melt, right? And that is being crystallizing in a certain depth. So that is why the temperature in this case is also high. And if we quench the granite quickly, that will produce extensional joint sets, which can occur in rhyolite, but not in applied. Applied is medium grain sized rock. It is not completely fine grained. So, yeah, but the thing is that the depth of occurrence of applied is much higher than pegmatite. Pegmatite is essentially forms in void regions where the differential stress is very much low, confining pressure is also low, and the movement is pretty much restricted. Even for applied when it is intruding as a dike, there will be some shearing and associated deformation during the flow of the dike. But for pegmatite to form, it is a completely static condition. We say this as say that as a quasi-static condition. So in that quasi-static condition, the pegmatite vein once the hydrothermal fluid is settled, it will precipitate the crystals, but it will definitely not show any deformation during the crystallization process. So that is why pegmatite uh, is an ideal candidate to occur within the joint sets. I mean, pegmatite itself, whether it can produce joint or not, that is a completely different issue. But it is certainly associated with existing joint sets in a host rock. So from that perspective, pegmatite will be a correct answer. But yes, applied is much fine grained than pegmatite. Bigmatite and pseudotachylite are also the incorrect options in this case. So the grain size difference can be considered for jointing if the joint sets are occurring within the rock type given in the options. Okay. So this was the first question. So now move on to the next question, which says a rock mass in an area is faulted. The fault surface shows slicken sides. If the rake of the slicken lines is 90 degrees, then the fault is a strike slip fault. Option B, normal fault. Option C, thrust fault. And option D, cannot be determined only from the rake.
It is a strike slip.
It is strike slip. No, actually, it will not be strike slip, because for strike slip, the net slip will be 0. Right? So if you have a fault surface, so if this is the fault plane, and this is the strike of the fault, right? So, and we observe that the slicken lines on the fault plane occurs like this. Right? So if this is the average orientation of the slicken lines, then this is the rake, and this orientation, if we give a direction, this is the net slip. So on a fault plane, the rake of the slicken lines provide the magnitude of the orientation of net slip, which can be used to determine the trend and plunge of the net slip. Now, if we classify the rake of net slip along different kinds of faults, so if we have oblique slip fault, we will have a fault plane like this. Right? So this is the net slip direction, and this is the strike. So for oblique slip fault, the rake of net slip is within the range of 0 to 90. For strike slip, so this is the net slip parallel to the strike. So rake of net slip is equal to 0. And for deep slip fault, this is the net slip, this is strike, and the angle is 90 degrees, right? So for deep slip fault, the angle is 90 degrees. So, and according to deep slip, it can be both a normal fault or it can even be
Thrust.
thrust fault. Both can occur. So obviously, if the rake of the slicken lines is 90 degree, the fault will be deep slip fault. But whether it is a normal fault or whether it is a thrust fault, it cannot be determined only from the rake. We also need the slicken sides, right? So if the fault surface containing slicken sides appear as steps like this. So there is a roughness on the slicken sides. The surface is rough and it appears as steps like this. So if this is the smoother side, and if this is the rougher side, so this will be the direction of displacement. So if we rub our palm over the fault surface along the rougher direction, so whichever direction will be rough. So if you have a fault surface that contains slicken sides, that means a fault plane that is engraved with slicken lines. So that is the definition of a slicken side, right? So if we rub our palm over the fault surface, so you will definitely have a smoother surface and a rougher surface. The direction along which the surface appears as rough is the direction along which the fault displacement has taken place. So now if you find that the roughness is opposite to the deep direction, that means the fault is definitely a thrust fault, right? So the movement will be opposite to the deep direction of the fault. And if the roughness is along the deep direction of the fault, then it is a normal fault. Okay? So we can write it here. Rough along deep direction. This is normal fault. Rough opposite to deep direction, that is thrust fault. So in this case, we can see that option D is correct, that we cannot determine the nature of the fault alone from the rake. Obviously, it is definitely a deep slip fault, but whether it is a thrust fault or normal fault, that information we need extra parameters such as the fault surface roughness, the direction and the orientation of the slicken lines, and then also we need to see the cross-sectional map of that region, geological map of the region, whether there is uh, repetition or omission of strata. Based on that, if there is a normal fault, there will be omission of strata. If there is a thrust fault, there will be repetition of strata. So these kind of statements we have to, or thumb rules we have to apply to surely determine what is the nature of the fault. Okay. So this was our second question. And this is the third question. An area shows linear erosional depression, sack pond, spring, and offset stream along the sub-horizontal slicken side. The prominent structure indicated by these features is option A, Strikely fault, option B, Horst and Graben, option C, Klippe, and option D, Nappe.
Option B, sir.
Horst and Graben. Why is that? Why are you saying that it will be Horst and Graben?
Sorry, it's linear erosion. Sir, एक second, sir, just a minute. It's strike slip fault.
Exactly.
Sorry.
So sub-horizontal slicken sites means we are talking about uh, a fault plane where the slicken lines is having a very low rate. That the slicken lines have a very gentle rate, which is close to zero. Right? So, and also we have option is, I mean, it has been given offset stream along sub-horizontal slicken lines. That means there is a stream that is going and there is an offset of the stream, and the exposed slicken lines are like this on the surface. So this is a stream, this is the offset, and the offset is along, I mean along means that is parallel to the sub-horizontal slicken lines. So that will definitely tell us that this is a strike slip fault setting. So option A is correct. Now moving on to the next question. A series of high angle reverse fault developed during developed between two thrust planes is known as option A Chopin structure, option B syntactic Pluton, option C syntaxial bend, and option D none of the above. So I must tell you that the option in this case, option A is correct. That is, this is the Chopin structure. So how these things happen? So if we just observe common fold thrust belt setting, so if this is our strata and it is subjected to I mean layer parallel shortening. So what happens is this case, in this fold thrust belt setting, that is in an orogenic belt, there exists a weak laminated plane that localizes the deformation, and that is called the decoloma. So the decoloma is essentially a detachment fault that localizes the strain during orogeny. And since the shortening is imposed over these layers, what will happen? The decoloma will bend and it will generate a thrust fault. And this is called the frontal thrust fault. Right. So this is the frontal thrust. Now for the thrust, in this case, the material will again go up the layers and they will create again a flat. It, it produces a ramp. From a flat, it produces a ramp and then again it goes into a flat. So we can say that this looks like this. So this is, if this is the strata, this will be the fault plane. So this will be the decoloma along which the initial thrust will occur. Right? Like in our case, we have the Himalayan orogenic belt. So we have the MFT, the main frontal thrust. So that is in the Shivalik region, and that is the region from where the Himalaya is basically, I mean, the orogenic polysional orogeny is taking place, and Himalaya is propagating its thrusts towards the south. So that is how the entire thrust planes are dipping towards north. Right? So what happens is that during this kind of uh, ramp structure, flat ramp flat geometry, in progressively deforming orogeny, polysional orogeny, we can have series of these thrust faults. So one thrust may generate, it accommodates the strain through thrust faults, and it once it again produces the ramp, the fault is terminated. So initially it detaches from the decoloma, it goes up, and then when it reaches the ramp, the fault is terminated. Again, there is another detachment fault from the decoloma. It produces another ramp, it goes up, again it terminates over the existing pre-existing flat, and it forms a structure like this. So it goes on serially until the entire foreland is divided into different segments like this. So these segments, they are known as the imbricate fault, imbricate thrusts or duplex. Right? Now, this is a result of a constant. This is a result of a constant strain rate deformation, right? So there is a no change in the uh, orogenic collision system. So the collision is taking place homogeneously with respect to time. That means there is no change or no sudden change in the strain rate or any localization other than these imbricate thrusts. So they will produce these thrust planes with similar dip. They will all dip towards the same direction, and the dip amount will more or less be same for each of these thrust duplexes. Okay? But if it happens in a case where after the initiation of the thrust, like when the main frontal thrust occurs, after that, during the successive phases of thrusting, if the strain rate or the deformation rate or even the velocity of the uh, detachment from the decolumn changes, as in it becomes faster, so the thrust faults will transform into reverse faults. So what is the difference between a thrust fault and a reverse fault? So both of them have the same slip direction, but a reverse fault has a dip of the fault plane higher, or I mean 60 degree or higher. So that is the definition of a reverse fault, right? A thrust fault essentially is a fault with a deep amount, generally lying from 15 to 30 or maximum 40 to 45 degrees. So that is the maximum limit of a thrust fault. But whenever we talk about reverse fault, that means it has a deep of it has a deep amount that exceeds 60 degree. So what will happen now if this is our initial configuration? Right, then we suddenly increase the velocity. So there will be series of high angle thrust faults like this. And then again it is bounded by another thrust fault. So if this is the main frontal thrust and this is the final thrust, this region with reverse fault, they will be called as Tupen complex. Okay. So one is duplex complex, another is Chopin complex. Duplex, we have consistent deformation. Every thrust fault has more or less a constant deep, right? But if we have the variation in the orogenic process, especially the rate of the process, then definitely we will be producing highly and steeply dipping uh, thrust faults that are also bounded by two normal thrust faults. So this arrangement is called the Chopin structure. This is not only controlled by the rate of deformation, but there is an important effect of the individual layer thickness, so which are being trusted over. Okay? So if you have a very variation in the thickness, you can end up producing high angle reverse faults and thrust faults simultaneously based on the thickness variation. Even if we are in the same stress regime, it can also happen in that case. Okay, so let us move on to our next question. Which of the following sequence of fault settings represents a decreasing release of energy during an earthquake? Option A, thrust, strike slip, normal fault. Option B, thrust, normal fault, strike slip fault. Option C, normal fault, thrust fault, then strike slip fault. Option D, strike slip fault, normal fault, then thrust fault.
I think his answer will be B.
Option D.
No. B for Bombay.
Yeah, exactly. Option D. Thrust is because thrust is something that requires more energy to deform, and that is why it has the higher capacity of storing energy. The strain energy that will be stored within the within a thrust system, it will be much higher. So normal fault is normal fault is mm,
Sir,
normal
in
fault in many cases it is gravity driven.
gravity driven, it's hanging
Mm,
wall is also effect of gravity is there. In thrust,
yes,
we have to work against the gravity.
exactly. So normal fault is I mean, and strike slip fault is basically neutral. So it seems the fault plane is itself uh, perpendicular or oblique, and there is no movement along or opposite to the attraction of gravity. So in that case, normal fault in many cases associated with gravity, but not actually not only gravity, because of the other thing. If you it is certainly a point. Thrust fault, thrusts on the other hand works opposite to gravity. So this is the very basic criteria, but this is not the most important. The most important thing is that compressive strength of a rock is much higher than the tensile strength. Right? So, in order to produce a normal fault, we need tensile stress, right? But in order to produce a thrust fault, we need a compressive stress, right? So that is why if we arrange in terms of the stress, so compressive stress is higher than the tensile strength, which is obviously higher than the shear strength. So this is the order. That means compressive strength, I mean, deformation which has the highest strain energy order. We will see thrust faults will have highest strain energy, then comes the normal fault, and then comes the strike slip fault, right? So that is why in terms of strain energy, thrust faults will have the highest energy compared to the normal faults or strike slip faults. And then again, in terms of dissipating energy, thrust will obviously release higher energy. So the amount of energy dissipation will be higher, will be highest in compressive failure. Compressive failure, then tensile failure, or right. So that is why thrust faults will be having higher energy dissipation than normal fault and strike slip fault. Right? Okay. So the next question: a fracture surface is curved. The rock mass enclosing the fracture plane shows relative displacement based on the sense of the curvature of the fracture plane. Select the possible correct statements based on the condition mentioned above. Purely concave surface will produce normal faults. Purely convex surface will produce thrust faults. Sigmoidal sense of curvature will produce thrust faults. Relative displacement is improbable along a purely convex surface. So this is a multiple select question. That means more than one options will be correct in this case. So in this case, then you have to select the all the correct options.
Purely concave surfaces produce the normal fault in listric fault, just like this.
Exactly. So option A is definitely correct. Yeah. So option A is definitely correct. If you have a curved fault surface, we can have normal faults. So this is a listric fault plane. Now, if I just have a surface like this, it is really not possible to slip over this surface. Neither it will be possible for normal faulting, nor it will be possible for reverse faulting or thrust faulting. Because if we have a surface like this, and there is a counterpart which is like this. So in order to move in this direction, there will be uh, difference in the stress along this curved surface. Right? So while this surface will try to slip faster, this portion will generate more friction and eventually impede the motion. And again, if we have a curved surface like this, and then we try to generate a thrust fault, that means if it's trying to move in this direction, obviously it will be having higher amount of friction experienced at the bottom part. So relative displacement is improbable along a purely convex surface. So in case of elliptic fault plane, the surface is concave, purely concave, right? Therefore, for a purely convex surface, relative displacement is improbable. But if we have a sigmoidal, so option D is also correct, that relative displacement is really improbable along a purely convex surface. But if we have a thrust plane like this, or rather not like this, if we have a thrust plane like this, that means it is already producing a flat ramp and flat geometry. Okay? So if this is a fault plane, so this is a sigmoidal fault plane, and which is producing a ramp, flat ramp structure. Definitely we can have thrust faults along this. So thrust faults can occur along a sigmoidal fault plane, right? So option C is also correct, but only option B is wrong. Purely convex surface will produce thrust faults. That is definitely wrong, because purely convex surface will, relative displacement along purely convex surface will be improbable. That's what we have discussed for the option D, right? So therefore, we can say that A, C, and D, these are the three correct options in this case. Okay, so moving on to the next question. In an experimental setup, a heterogeneous differential stress is applied along with a finite confining pressure. As a result, the three principal stress components are unequal. Which of the following parameters is or are required to closely estimate the failure criterion of the rock? Option A, the coefficient of internal friction. Option B, the first stress invariant. Option C, the second stress invariant. And option D, yield strength of the rock at different confining pressure and the second stress invariant at each field stress. Okay, so
Uh,
yes, are you saying something?
no, please continue.
Okay, so in this case, we will the important information that is given. First of all, heterogeneous differential stress is applied along with the finite confining pressure. So we have a finite confining pressure, right? Sorry. That means this is the sigma mean. This is given, and we can vary this value. There can be sigma bar 1, sigma bar 2, sigma bar 3, and so on. So we have this in control. So the experiment can have a controlled value of finite confining pressure. Now heterogeneous differential stress is applied. That means the deviatoric stress is heterogeneous, means sigma 1 minus sigma 2 is not equal to sigma 1 minus sigma 3 is not equal to sigma 2 minus sigma 3. Okay, and as a result, sigma 1 is not equal to sigma 2 and it is not equal to sigma 3, and both of all these pairs are greater than 0, right? So in this kind of so this defines a polyaxial condition, right? So in a polyaxial condition with a finite confining pressure, we can only utilize the von Mises criterion, failure criterion in this case. In a polyaxial condition with finite confining pressure, only the von Mises criterion can be applied to estimate the state of failure, right? Now, why not we will why not we can use the Moore Coulomb criterion, or why not we can use the Tresca criterion, or why not we can use the Hoek Brown criteria? Because in all of these other failure criteria, one thing is assumed that sigma 1 is not equal to sigma 2, which is equal to sigma 3, and these are greater than 0. Right? And that means there is that is an isotropic differential stress. But in this condition, the differential stress is heterogeneous and it is not isotropic. So that is why we cannot apply the Hoek-Brown criteria or the Moore-Coulomb criteria or the Tresca criteria in this case to assess the failure condition, the state of failure. So we have to apply the von Mises criterion. So what is the von Mises? What does the von Mises criteria say? That sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square should be less equals to 2 sigma y square, right? So this is the von Mises criteria. That means, and this is the second invariant, second stress invariant. Right? I2. So I2 should be less equal to yield strength. And when the second invariant becomes equal to the yield strength, that time the rock mass fails, right? So in order to actually estimate the failure criteria or the failure envelope, we have to conduct the experiment at different confining pressures, then determine the yield strength at different confining pressures, and also from the differential stress data, we have to estimate the second invariant. Then we calculate the second invariant at each of these confining pressure, the associated yield strength in that confining pressure, and the associated differential stresses at that condition. Put together all these parameters, if we follow the von Mises criterion, only then we can estimate or we can define the failure envelope or the state of failure for the material that we're talking about, right? So with
D.
only the information about the second stress invariant I2, it is not uh, appropriate, or I mean, uh, it is complete information. Coefficient of internal friction has nothing to do with the confining pressure, because coefficient of internal friction is a material property that remains more or less constant. The only thing that can change is the shear stress component. It can change according to the confining pressure, but it has nothing to do with the coefficient of internal friction. The first stress invariant itself is the confining pressure, the mean pressure. So that is of no use because you are actually controlling the confining pressure in the first place. So the only probable option that remains is the yield strength of the rock at different confining pressure and the second stress invariant at each of these yield stress to actually define the failure criteria. So option D is the correct option. Okay, so let us move on to the next question. Question number 8. A coarse-grained granite block is subjected to an isotropic confinement with a minimum stress of 25 megapascal. The uniaxial compressive strength of the rock is 150 MPa. If the rock contains pre-existing shear fractures, then find the range of possible different stresses required to localize deformation into these rock mass. So if you follow thoroughly, you will find that the very statement, the very first condition is given, that is isotropic confinement. Now, isotropic confinement means that sigma 1, which is not equal to sigma 2, but sigma 2 is equal to sigma 3, and all of the condition is greater than 0. That means if I have a rock cylinder like this, and if I am applying sigma 1 from here, sigma 2 from here, and sigma 3 from here, so differential stress along this plane and the differential stress along this plane. So if this is an orientation of the plane, and this is another orientation of the plane. So the differential stress along both of these planes will be the same, because sigma 1 minus sigma 3 will be equal to sigma 1 minus sigma 3. This is the condition for isotropic confinement, right? So in this case, we can apply the failure for identifying the failure criteria. So then the question says that find the range of possible differential stresses required to localize deformation into the rock mass. So localizing the deformation means that there is a failure. Right? Either it is a shear failure, either it is a tensile failure, whatever it can be. Now, which of the following failure criteria associates the uniaxial strength of the rock with the failure criteria? So we have the Hoek-Brown criteria, that associates uniaxial compressive strength of the material with its failure at confinement. And the formula is that the maximum principal stress required is the summation of the minimum principal stress followed by MC0 plus, sorry, MC0 sigma 3 plus SC0 square. This is the Hoek-Brown criteria, where M is an empirical coefficient, C0 is the uniaxial compressive strength, right? So this is the value is given. S is another empirical coefficient. Now, if the rock is intact, that means it has full cohesion with no existing fractures or no nothing. S will be 1. And if the rock is non-intact, then S will be 0. In our case, if it is given that if the rock contains pre-existing shear fractures, then definitely we have to put S is equal to 0. That means we have sigma 1 is equal to sigma 3 plus root over of m c0 sigma 3. That's it. So sigma 1 minus sigma 3, it is the differential stress. So the value of differential stress del sigma is basically root over of m c0 sigma 3. Now there are possible ranges of m values. For coarse grain material like granite, m can range between 22 to 33.
33.
Exactly. So sigma 1 22, we will have root over of 22 times 25 times 150, and sigma del sigma 33, we will have 33 times 25 times 150. So these are the two values which will provide the range of the differential stress for this rock, granite rock, to fail under a given confining pressure. Okay, so you can calculate the value. You can have so the differential stress in this case will be 287 MPa, and it will be 352 MPa. Okay, so let us move on to the next question. In a complex translational tectonic setup, a conjugate strike-slip fault pair evolves from right stepping shear to left stepping shear. Choose the correct sequence of geomorphic evolution along the strike of the entire fault network. Option A, contractional ridge transform fault, pull apart basin. Option B, transform fault to contractional ridge to pull apart basin. Option C, pull apart basin, transform fault, then to contractional ridge. Option D, pull apart basin, then transform fault, then again pull apart basin. So,
Sir, a left stepping or right stepping, it means
sorry, I can't hear you. Can you repeat again?
this left side, right side, sinistral, dextral is.
Your voice is breaking. Can you write in the chat box?
Sir, network is weak. Network is weak.
Oh, okay. So can you repeat again? Now I can hear you.
Right, left.
So
In
the
right side,
concept
right.
is yes, yes,
See,
tell.
see, right side is the pull apart basin, and left side is ridges is there in between transform fault.
Hmm.
You see, answer will be there, I suppose.
Exactly. Yes, yes, exactly. Option C is correct. So if we have, say, for example, continental trans transpirational setting, where we have two conjugate networks of faults. Okay. So if this is right stepping and if this is left stepping, then this is the region in between. So in this portion, what will happen if this is the zone of overlap? So for right stepping, this block, it will move in this direction, and this block, it will move along this direction. So as a result, we will find a lens shaped extensional feature, and that will be a pull apart basin. So this will be a pull apart basin. This pull apart basin is being transformed through a transform fault. In this section, we will see no geomorphic feature. It will simply be a strike slip fault. Then again, we come to the left setting where we have this certain overlap. This is left setting or left stepping. So this block is moving in this direction, and this block, it is moving in this direction. So the overlap zone, they will produce ridges like this. So this is the right stepping. And this is the left stepping setting. So in this case, it will produce contractional ridge. So the correct sequence will be pull apart basin to transform fault to contractional ridge. So this is a setting for a dextral strike slip fault. The opposite will happen if we have a sinistrial strike slip fault with conjugate pair of different stepping then we may find a contractional ridge followed by a transform fault, then followed by a pull apart basin. Reverse will happen if we reverse the sense of shear. Okay. The next question says, choose the correct statement regarding the relationship between bedding parallel joint spacing, layer length to thickness ratio, and material stiffness. Option A, highest stiffness and highest length to thickness ratio produces highest joint spacing. Highest stiffness and lowest length to thickness ratio produces highest joint spacing. Then option C, lowest stiffness and lowest length to thickness ratio produces highest joint spacing, and lowest stiffness and highest length to thickness ratio produces lowest joint spacing.
I think it's A is correct.
I think option A is not correct. Let me explain why. So there are two different things you have to consider. So first of all is the effect of stiffness. If I just discuss effect of on joint spacing. So joint spacing, the parameter delta is proportional to the stiffness of the layer. Sorry, inversely proportional to the stiffness of the layer. And joint spacing is directly proportional to the layer thickness. Okay. So these are the two information that we have. And how they are related.
Sir,
So if I
sir,
just plot,
sir, during our
yes,
video lecture, it was
yes,
given in if we have three layers: weak layer, a very weak layer, and stiff
mm,
layer. The maximum
mm.
joint spacing is in a stiff layer.
No, maximum joint spacing means
Bedding
the
bedding parallel joints is shown in stiff layer in slide 10 of the lecture.
yes, but I mean, so the stiffness, the bedding plane, I mean, the spacing bedding parallel joints. Mm,
If you do you have that lecture?
yeah, let me see.
The spacing
Just
of
let me see.
in
Mm.
the lecture 28, slide 10.
Mm. Okay, okay. Checking. Yeah, so stiffer layer will produce more closely spaced joints. Yeah, that is correct. Yeah, I saw that picture. So it was like this. So you have very weak layer, we have stiff layer, and we have weak layer. So in the stiffer layer, the spacing will be much smaller. Compared to weak layer, we have larger
Okay,
spacing, and very weak layer will have very large spacing.
okay. Number of joints will be more in a stiff layer.
Exactly. Number of joints will be more in the stiff layer. That means the spacing is less. So the joint spacing is inversely proportional to the stiffness of the material. So now, and another thing is that if I have the layer thickness plotted against the joint spacing, you will see a non-linear curve like this. So if we have higher thickness, higher layer thickness, we will have higher joint spacing, right? So that is how joint spacing is proportional to layer thickness. Now, since it is proportional to layer thickness, now if I say that the option is given as layer length to thickness ratio, it is not directly talking about thickness of the layer, but it is talking about length to thickness ratio. So if I have high length to thickness ratio, that will mean my thickness is low. But if we have low length to thickness ratio, that means we will have high thickness. So joint spacing in this case is inversely proportional to the L is to T value. If I have high L is to T ratio, that means it will have low thickness and the joint spacing will increase, decrease. And if I have low L to no high L to T ratio means it has low thickness, then the joint spacing will be low. And if we have low length to thickness ratio, that means the thickness is high, then the joint spacing will increase. So I guess
Then it will D will be lowest stiffness, the highest. No.
so if we follow this relation, so we have this information. We have the joint spacing inversely proportional to the length and thickness ratio, and joint spacing inversely proportional to the stiffness of the material. So if I have a combination like this, so if I draw a checkerboard,
Right, then it will be D. It will be D.
lowest stiffness and high length to thickness ratio produces lowest joint spacing. No, there is a catch. So um, we can plot it like this. So if I say that I have three axes. One is 1 by L to T, and another one is 1 by stiffness, right? So we can see that if I increase this ratio, that means I am decreasing the thickness, right? And if I increase the value of S, that means I am decreasing the ratio. So according to the first theory, and the third axis is the joint spacing, right? So if I have highest stiffness and highest length to thickness ratio, so this value is maximum and this value is minimum, right? 1 by S is minimum because I have the highest stiffness, so 1 by S is minimum, and highest length to thickness ratio, so this is also minimum, sorry, so this is also minimum. This is also minimum. If we project it on the third axis, we will get a point like this. So it is most definitely not the highest joint spacing. Are you getting this, what I am trying to convey? So option A will not be correct. Now second option, highest stiffness and lowest length to thickness ratio. So we have the highest stiffness, that means it is still plotting here, but the lowest L to T ratio, that means the value will be here. So we project it here and we project it here. So the value will lie around in the midpoint of these two projections. So it will be somewhere here. Okay. And then this is not the case again. Now we have lowest stiffness and lowest length to thickness ratio produces highest joint spacing. So we have lowest stiffness, that means 1 by S will be highest, and lowest length to thickness ratio, that means 1 by LT will be also highest. So if we project from here and we also project from here, we will get a point here, right? And then lowest stiffness and highest length to thickness ratio produces. So if I have the lowest stiffness, that means the point still here, which will produce, projecting over here, but the highest L to T thickness, that means the point will plot here. So the projection will be here. So the ultimate value will be lying and around the midpoint of this projection. So only if I have the lowest length to thickness ratio and the lowest stiffness, the ultimate projection will be closest to the highest joint spacing. So that is why option C is correct. Okay, so since we are running out of time, we have also 6 more questions left. So let us move on to the next question. Which of the following statement is correct regarding a joint plane feature? High fracture propagation velocity at a low differential stress produces symmetric transitional marks. High fracture propagation velocity at a high differential stress produces symmetric rib mark. Option C, intermediate fracture propagation velocity at an intermediate differential stress produces plemo structure. And option D, Slow fracture propagation velocity at an intermediate differential space produces asymmetric transitional mark. So the concept is that if we plot the fracture propagation velocity with respect to the differential space, we can have three states of velocity like this. This is regime 1, this is regime 2, and this is again regime 3. So regime 1 is high velocity, low stress. Regime 2 is low velocity, intermediate stress. And regime 3, it is high velocity, high stress. So with increasing the regime order, we are increasing the asymmetry of joint features. So in the first regime, since it is the most symmetric, we will produce the rib marks. Since it is intermediately symmetric, we will produce slightly asymmetric transition marks. And in the regime 3, we will produce highly asymmetric plumose. So here we will have concentric rib marks. Here we will have the rings of the rib along with some plumose. And here we will have definitely the plumose structures. Okay. So asymmetry in the sense of the nucleation point to the propagation direction, towards the propagation direction, that in that direction the asymmetry may increase based on the fracture propagation velocity. So if we follow this observation, only option B is the correct answer, because slow fracture propagation velocity at an intermediate differential space will produce asymmetric transition marks in regime 2. Okay. Moving on to next question. Which of the following statement correctly defines a window and a clipping? Option A, allochthonous exposure within autochthonous rocks and autochthonous rock exposure within an allochthonous rocks. Option B, autochthonous exposure within allochthonous rocks and allochthonous exposure within autochthonous rocks. Option C, allochthonous exposure within autochthonous rocks and the exposure opposite to the minimum displacement of the fault. And option D, autochthonous exposure within the allochthonous rocks and the exposure towards the minimum displacement of the fault. So if I see thrust nappe like this, so these are older in situ rocks, which is also known as autochthonous. These are thrusted older rocks not in situ. So this is basically a thrust sheet. So these are the allochthonous rocks. Now, if erosion takes place, then this part may be get eroded and the autochthonous unit may be exposed here. And similarly, sorry, this entire part may get eroded except for a place where the allochthonous may exist, and after erosion this may come up, may get exposed. So the autochthonous rock may get exposed and a small patch of allochthonous rock may remain in this region. And similarly, we can have a counter part of this where the erosion takes place like this and the autochthonous rock may get exposed surrounded by the allochthonous rocks. Right? So if the thing is that the allochthonous rock is surrounded by autochthonous rock, it is defined as
Clip.
clippe. So this is a clippe.
Just like outlier.
And if exactly just like outlier, and if the autochthonous rock is exposed surrounded by the allochthonous rocks, that is known as the window. So option B is correct because at autochthonous rock exposure within allochthonous rock is definitely a window, and allochthonous exposure within the autochthonous rock is definitely the clippe. So this is how the definition is. Moving on to the next question. A fault plane has an attitude of 030 40 degrees southeast. The attitude of the bedding plane in the host rock is 040 45 degrees southeast. So if I just draw a stereogram, one plane is 030 40 degrees southeast, another is 040 45 degree southeast. So this is fault plane and this is the bedding plane. This is their intersection point, and this has the plunge amount will be nearly about 40 degree and plunge direction will be definitely between 120 to 130 degree, right? Now it is given that if the rake of the slicken lines on the fault plane is 90 degree, so if this is the fault plane and if we go 90 degree like this, then the fault can be classified as option A, strike slip fault, oblique slip fault, trace fault, and none of the above. So I have a fault plane and I have slicken lines which are at 90 degree with the fault plane. So this is the strike. That means the intersection point between the bedding plane and the fault plane produces the same lineation parallel to the slicken lines. and rake is 90°. Therefore, the fault is deep slip. Right? So, if I have a fault plane like this, and the bedding planes are also parallel, more or less parallel to the fault plane, like this, we will say no offset in the bedding plane in this case, because the fault plane is in more or less parallel to the bedding plane, and also the fault is a deep slip fault. So purely deep slip fault will never have a heave or horizontal throw, and it will definitely cause bedding parallel movement. I mean, if the bedding planes are sloping like this, it will cause bedding parallel movement, and in that case, we will not get any offset from that fault. These kind of faults are known as trace faults. So bedding, so in this case, the fault trace will not leave any offset. Okay, so you cannot, you will not be able to distinguish between the bedding plane and the fault plane. Only if you find an exposure of a fault scarp, then you can confirm, okay, so there might be a fault. But other than that, trace faults are such faults in where you cannot find the offset. Okay, so moving on to the next question. In an oblique slip fault having 30° deep, the net slip is 10 meter at an angle of 45° to the strike of the fault plane. The deep slip component of the fault plane is given in meters. So as we know that if this is our strike slip component, this is our net slip component, and if this angle is theta, this is the deep slip component. So deep slip is equal to net slip times sine of theta. Therefore, deep slip will be 10 into sine 45°. Nearly about 10 by 4.1.414. 7.1 meters. So given the angle, this is the rate. So the rake is 45°, and then we can determine the deep slip, which is as 7.1 meters. Okay. The next question. Deep of a fault plane is 30°. If the horizontal and vertical throw of the fault is 45 meters and 100 meters respectively, then calculate the net slip of the fault with the rake of the slicken lines on the fault plane. So deep amount is 30°, right? And we have that if this is the deep slip component, if this is the heave of the fault, and if this is the throw of the fault, then we can say that the throw by heave ratio of the fault is tan theta. So if this is theta, so 100 by heave is equal to 1 by root 3, or heave is 100 root 3. So it is nearly about 173 meters, right? And this is the vertical section of the fault. For horizontal section of the fault, we have strike slip, we have horizontal throw, and we have the heave. And the relation is that strike slip will be root over of horizontal throw square minus heave square. There is some problem, I guess. The value will not be according to. Uh, so we can consider this as 245 meters. Otherwise, it will be a problem to consider. So 245 square minus 173 square. So it is nearly about 173 meters as well. So the strike slip component is 173 meters. And we can also calculate the deep slip of the fault. So deep slip will basically be so heave by cos theta. This is the relation. That means or it is better to use the sine theta. Because the deep slip will be throw by sine theta. That means 100 divided by half is 200 meter. So strike slip is 173 meters and deep slip is 100 200 meters. So net slip will be determined as root over of strike slip square plus deep slip square. That means 200 square plus 173 square. That means the net slip will be around 264 meters. And finally, this was the 15th question. Finally, if I say about the 16th question, a rock is subjected to high differential stress under high confining pressure. Upon crossing the yield point, on which of the following conditions the material will develop a brittle ductile localization? Option A, strain hardening. Option B, strain softening. Option C, strain independent plasticity, and D, none of the above. So if I plot the stress versus strain diagram of a material, so following the yield point, from the yield point, we can go up here and we can have homogeneous plastic deformation. Or we can go down here and we can have heterogeneous localization, right? And in between, there will be homogeneous shortening. So this is ideal plastic. This is strain hardening. And this is strain softening. So the idea is, if you want to localize the deformation or localize the strain in a smaller region, that is a ductile shear zone or in a brittle ductile shear zone, you have to have a initial strain softening phenomena. Otherwise, we will get homogeneous plastic deformation without any heterogeneity in the system. So option B is correct, that an amount of strain softening is required to initiate the localization in a deformation. So that was it. It was the end of 10th week. Now I have to say that I will take the 11th week's class on this coming Monday, that is 30th September. It will not be held on 5th October, sorry. Instead of 5th October, the class will be shifted to 30th September, that is this coming Monday from 4 p.m. to 6 p.m. I have already notified the NPTEL team, and I guess they will provide the email shortly to you. But since you are here, I want to share that the next class will be on Monday instead of Saturday. Monday from 4 p.m. to 6 p.m. Okay. And the 12th week's class is also postponed. It is postponed to 16th October instead of 12th October. The last week's class is shifted to 16th October, 4 p.m. to 6 p.m. I will be on field, so that is why I will not be able to take the class during the regular Saturday period. So I have preponed and postponed the class accordingly. So if you are available on the Monday, that is 30th September, we will have our week 11 class.
Okay, sir.
Okay. Thank you very much. So,
Sir, just a question. Just a question.
Yeah.
Which field you are going? Just a person.
I'm going in Himachal. I'm going in Himachal Pradesh.
So
I will be working on the thrust faults on the Himalaya.
Okay.
Okay. Thank you. Yeah. Bye.